Thank you for that introduction. And let me say it's a pleasure being here. This is my first visit to Lisbon, and had the chance to have dinner in Old City last night and made new friends, enjoyed some fantastic cuisine, and I am all in for the second Lisbon conference. We'll call it the WIFE conference. So I'm looking forward to coming back in the future. And let's see here. So I was asked to speak today on the greenhouse gas emission reduction capability of using the high viscosity asphalt rubber. And when I have typically high viscosity asphalt rubber is known as the field blend wet process. And as a comment, some of the nomenclature surrounding these products, terminal blend, high viscosity, no agitation, some of the nomenclature has gotten a little bit complicated. I like high viscosity asphalt rubber because it describes the product, not the process that's making it. So here's an overview of my presentation today. I want to talk a little bit about who CEI is relative to our overall parent corporate structure, talk about greenhouse gas reduction, talk about pavement performance, and then look in detail about the field blend wet process reviewed in some detail and show you some facility case studies, and then conclude with some quantitative data on the greenhouse gas reduction effect. So CEI Enterprises is one of 18 companies within the Aztec Industries family of companies. We specialize in the heating, storage, and processing of liquid asphalt, anything to do with bitumen. Our company handles. We're part of the Aztec Energy Group, which includes a sister company, Heat Tech, Jeffco, Powerflame, Peterson. And the company is organized along the lines of an infrastructure group, which is hot mix asphalt and paving plants, and then an aggregate and mining group. So in total, there are 18 companies. We're a publicly traded company. About 40% of our revenues are outside of the United States. We have facilities in Canada, Brazil, South Africa, Germany, and Ireland. So this is just an initial treatment of how asphalt rubber reduces greenhouse gases. And one of the biggest impacts is simply because by using a thinner paving thickness, you're reducing the aggregate haul, therefore using less energy and producing less greenhouse gases. The reduced cracking and rutting gives a longer pavement life, which then results in reduced maintenance incidents and cost. And there's some interesting studies that have been coming out recently regarding the effect of smoother pavement having a reduced rolling resistance on the automobiles and vehicle traffic on the pavements, therefore improving fuel economy and reducing CO2. And then not to be overlooked is the fact that it is genuinely the highest and best use of recycled tires when compared with more typical traditional methods of landfill, daily cover, and tire-derived fuel. So we've talked quite a bit in the last day and a half about the environmental factors, but the utilization of tires into the roadways presents a significant outlet for these end-of-life tires. And to put this in perspective, the Rubber Pavements Association figured a few years ago that over the life of that organization, its members had utilized enough tires and rubber to connect Prudhoe Bay, Alaska with Washington, D.C. And that's a distance of 4,500 miles or about 7,600 kilometers. And to put that in perspective in the European geography, that would basically be a tire road from Lisbon to St. Petersburg and back. So clearly there's a lot of opportunity to utilize tires in a very useful fashion. So the history of asphalt rubber has been covered in some detail. The introduction of the technology by Charles McDonald is well documented, and As far as the field blend wet process, there is an ASTM definition, and it basically says that you're using 15% or more of crumb rubber by weight. And then most U.S. agencies, and I'm specifically referring to California and Arizona, have a target of 19 to 21% crumb rubber. That's a typical utilization range. The specifications call for 18 to 22%. And the minimum target viscosity that they're trying to achieve is 1,500 centipoise. So successful production of asphalt rubber is clearly a matter of proper heat management. And that's been touched on in the past here. The virgin asphalt temperature needs to be at least 190 degrees C, which is 375 degrees Fahrenheit. And actually, that's the Caltrans minimum specification. Most of the blenders in the field like to have the virgin asphalt even hotter than that, as much as 220 degrees Celsius, simply because of the cooling effect that occurs when the rubber is introduced into the asphalt. Aggregate temperatures are typically less than 163 degrees C, and at the breakdown roller, about 143 degrees. And there are specifications in California that necessitate that the ambient temperatures be greater than 13 degrees C in order to properly pave with rubber-modified asphalt. So this picture just shows the fact that the crumb rubber does not dissolve into the asphalt rubber. The sample on the right could be virgin asphalt, or it could even be the terminal blend type material that Wright Process has put into the marketplace. But crumb rubber with 18 to 20% crumb rubber has an oatmeal type effect. Or I don't know if you have oatmeal here, maybe it's Berker muesli, but it's chunky looking material. And this chart shows just the basic reaction. You could spend a whole half hour to an hour talking about this, but it just basically traces what happens to the rubber particle from the initial onset as the rubber particle absorbs asphaltenes, the aromatic oils in the asphalt. You get a swelling effect and an eventual gel surrounding the rubber particle. And this is what leads to the viscosity increase during the digestion process. And I think someone showed this slide yesterday. Again, coupled with the other slide, you could spend a lot of time discussing this, but this basically shows over time the increase in the viscosity of the material. And we're noting here that the average viscosity of paving grade asphalt is 45 to 60 centipoise. That's before the introduction of the crumb rubber. So what happens with time and temperature, you have a rapid increase in the viscosity, reaching a peak, and then there's a slow degrade over time, but not nearly as rapid decrease in the viscosity as on the upside. So the phenomenon occurs because of the temperature of the material, the reaction time, and there are other qualities, whether you're using a chirogenic produced crumb rubber or ambient grind. All has to do with the surface area characteristics of the rubber particle and how rapidly and effectively it absorbs the asphaltenes. And of course, the nature of the asphalt is a key characteristic also. So I think George Way covered the performance benefits of the material quite well yesterday. But I did want to show these slides. These are some field slides. This was a residential street in Indio, California, which is near Palm Springs. It's a hot desert climate. Ambient temperatures in the summer are 40, 45 degrees Celsius, or upwards of 110 to 120 degrees Fahrenheit. And you can see the old pavement is very cracked. There was a slightly less than 2-inch overlay of rubber modified asphalt installed. It's about 45 millimeters, with the result that years later, when this picture was taken, not that picture, this picture, that you had a very satisfactorily performing surface. And here's another application of asphalt rubber. This is a chip seal, which is just a spray applied surface treatment. This is done on again, a residential street, and you can see it was the street as just before the application in 1981, 19 years later in 2010, the project was performing quite well. So 19-year life with this material is excellent cost reduction maintenance treatment for this municipality. And you can't talk about the product without noting not only the skid resistance, but the visibility safety. And we saw this slide yesterday. There's actually a movie, it may be on the Rubber Pavement Association website, but it's a video that someone took driving down the highway where they're on, I think it's a concrete surface, spray on the windshield, driving into a rubber asphalt gap-graded section, and the spray ceased. So it's a dramatic representation of the safety benefits of the visibility improvement. So now I want to turn to a more detailed look at the process, augment some of the points that Louis touched on earlier. CEI built their first rubber plant in 1992. Since that time, we've constructed approximately 60 of these plants. Over the years, the design and the characteristics have changed, as have the production capabilities and some of the environmental aspects. But the system is basically comprised of 2 units. And the units I'll show here initially are mobile units meant to be moved from job to job. But the first trailer is the mixing blending unit, and the second is the reaction tank. And so at this point, we're going to look at the process flow, and my associate, Stuart Baker, is going to pass out some samples of rubber that are used in this process, just so you see visually some of the type of material that's being used. Stuart accompanied me on the trip today. He's our post-production manager. I can tell you how these plants are supposed to work. Stuart can tell you how they actually work. So, Stuart gets to go out in the field and make them work. So we're dealing with, in the case of these California plants, 2 dry materials and 2 wet materials. And so we have 2 rubber feed hoppers and that are mounted on load cells. So we get a loss weight indication during the production process to measure the flow of the crumb rubber. So the larger hopper, in California, 75% of the rubber used is a crumb rubber, and that's the coarser sample that you see there. And the mesh size, that material is 100% passing to 10 mesh, which is 2,000 microns. There's 16% passing to 30 mesh, which is a 600 micron size. That gives you some idea of the coarseness. So 75% of the rubber is this crumb rubber, and 25%, the balance, is what we call high natural, or the truck tire rubber, that has a higher high natural content. And that material is 100% passing the 1,200 micron screen size, 78% passing the minus 30 mesh, or 600 microns. So it's a finer material. I might note that Arizona only requires the coarser rubber. But California feels that the higher rubber, the higher high natural rubber content provided by the high natural material provides for a more stable product and increases the viscosity in that previous curve. So we add the rubber into these hoppers, and the process weighs that material as the rubber is conveyed from the hopper into this incline auger up into the initial mixing vessel. Now we have some of our clients, particularly surface treatment people who are not putting high natural into this hopper. They're putting in a polymer. And their proprietary blends they've developed, they don't like to talk about what kind of polymer, and they've indicated to me that they're using sometimes 1.5% to 2%, but it is possible to use a different material in that second hopper. So having gotten the rubber into the mixing can, we turn then to the liquid asphalt introduction to the system. We put a heat exchanger on the plant, and that heat exchanger is designed to give the user a 100-degree F delta T on his incoming asphalt. Asphalt typically can be delivered at about 325 degrees, which is 163 degrees C. Caltrans has a requirement, as I mentioned earlier, of 375 degrees or 190 degrees. And most producers will heat the asphalt up to somewhere over 400 degrees, maybe even as high as 425 degrees, simply because at times there can be as much as a 50-degree drop in the asphalt temperature when that rubber is introduced. The rubber is at ambient temperature, so that will have a temperature reduction effect on the liquid asphalt. So the heat exchanger is here. We use a large heater for supplying the thermal fluid, and the thermal fluid from the system goes first to the heat exchanger and then throughout the rest of the process to heat the lines and the pumps and to keep the reactive material in the reaction tank hot and at the proper temperature. So just a comment here on the production rate of this plant. We work with some very large high production producers in California, particularly in Southern California, where the weather is good for, it's essentially a 12-month paving season, depending on the incidence of wet weather in January and February. But we have some producers there who will make upwards of a million tons of hot mix a year out of a single facility. And so they're very much production oriented. So the production capacity of this plant is designed to supply 35 tons an hour of reacted bitumen to the hot mix plant. And, oh, okay. Well, I didn't complete the cycle. The material that's, asphalt after it comes out of the heat exchanger goes through a Coriolis meter, a micromotion meter. So this gives us flow indication to match, so we keep the chrome rubber percentages and the asphalt in compliance. It's a recipe-driven formula. So in this mixing can, we have a Coriolis meter, we have a coils mixer. It's powered by a 30 horsepower motor. It rotates it up to 3,600 RPM. And it's really like a milkshake mixer. It creates a vortex of material. And its sole purpose is to combine the crumb rubber with the asphalt in order that that mixture can then be pumped over into the reaction tank. So in the reaction tank, this is where we're doing the digestion of the material. California requires a 45-minute reaction time. Arizona requires a 60-minute reaction time, just different specification. So now this tank is it's 24,000 gallons, which is roughly I think about 80,000 liters. And to address the whole production issue, if this was a single compartment tank, we'd have to do three things in that tank before the material could go to the hot mix plant. The first thing is we would have to fill the tank up to a level desired and then start the reaction process. Caltrans requires that you don't get credit for the first amount of material going into the tank. You only get credit towards the reaction time when you put in the desired amount of material. So in this case, 24,000 gallons would take, it'd take about an hour and a half to fill up. So you'd be an hour and a half to fill it up, then you'd have to react it for 45 minutes, and then you could start delivering the material to the hot mix plant. So again, in working with these high production producers in Southern California, for years we were supplying a 2-compartment tank. And at some point, with a producer who was trying to achieve production rate on the order of 450 to 460 tons an hour, we devised a 3-compartment tank. So basically, and each compartment is 8,000 gallons at 35 tons an hour. It takes in a 45-minute reaction time. You can fill an 8,000 gallon compartment, 24,000 liters, in 45 minutes. So at the top end production rate, he can drain a compartment in 45 minutes. So basically what you have here then is an equilibrium situation where you fill a compartment in 24 or 45 minutes, you react a compartment in 45 minutes, and you're draining a compartment in 45 minutes. And that's actually 3 steps, and that occurs in each compartment sequentially. So this was our solution to meeting production requirements for high volume producers. But the same principle applies to smaller plants where if you wanted, you only needed to, say, make 10 tons an hour for a 100 ton per hour producer, this same concept would apply there as opposed to having 1 or 2 tanks to try and balance out your whole production situation. Some other things we have to do in these plants for Southern California is a very environmentally conscious area. We have vent condensers that are air conditioned and even have a second phase of collection with an electrostatic precipitator. And this is to pull the blue smoke fumes off the emission points on the tank, and as well as vent the inside of the tank to capture these fumes to reduce not only the visible emissions, but reduce the odor that results from those blue smoke fumes. This is a look inside the tank. There have been some questions raised today about mixing in horizontal tanks, vertical tanks. In these horizontal tanks, we're using a 24-inch auger. It's a closed blade, so we're pushing the material into the middle and forcing the material through the heating coils, which serves the purpose of facilitating the heat transfer to the material and also keeping the coils clean over time. It's a very effective mixing technique. So, and then after the material is reacted, it's pumped off to the asphalt plant and utilized. So these are some pictures of actual plants. This is a plant that's actually operated by a company that has 6 rubber plants. They are a subcontractor. They move from project to project to blend material for customers they've bid projects to. And that's a picture of a super sack. The material is always supplied in 2,000-pound, 1-ton sacks. This material is supplied by a company called CRM, Crum Rubber Manufacturers. Some of you in the audience may know Dr. Barry Takalu, who is the owner and founder of CRM. And not only is he, I think, the largest rubber producer in, or ground tire rubber producer in North America, he's also a world-recognized authority on the tire recycling business and utilization of rubber in asphalt. Here's another plant. This is owned by it's actually a single plant, single asphalt plant operator. Business in California has been so good the last few years that the contract blenders can't get around to all the projects. Consequently, we're seeing more people who, while not necessarily having that large a production requirement for rubber in any given year, they need to have their own production capacity to keep control of their jobs. people frequently ask me, how many tons do you have to produce in a given year to make the investment in a rubber plant practical? Well, there's several ways to look at that, and there have been some interesting stories recently where, and I can think of one company in the Bay Area that was ready to start a 200,000 ton freeway overlay job, and they couldn't get any of the people that had bid them to blend rubber to come in on the job, and they ended up having to go with a very expensive alternative to satisfy their requirements for that particular job. So we see in California, it's my vision that as years go on, more and more plants, and possibly even to the point of all plants, will have a rubber blending facility located permanently at their plant. This is a plant we supplied for Boral Resources in Australia. It's a little different design. They utilized this plant for chip seal applications, so they needed something that was a little bit more transportable, and they didn't need a very high production rate. This is sized for 15 metric tons an hour. Now, here's a plant that we just recently supplied for Constructora El Condor, and headquartered in Medellin, Colombia. This plant is set up in the eastern side of the country of Colombia near the Venezuelan border. It's a 15 ton per hour plant, and it's built on flat rack platform. So it's easily transportable. There are no wheels underneath it, but it's easy to pick it up and put it on a truck and move it. So in this particular plant, I think you can see a little better, we have two 6,000 gallon reaction tanks. We have the heater and the heat exchanger on this load, and the single rubber hopper on this load with the attendant pumps and meters and so on in the control panel. El Condor has a 1,000 kilometer, it's a 100 kilometer concession job, and they're rehabilitating the roadway. There you see they're putting down a new aggregate base. They're paving, and then they're going to cap this off with a 2-inch rubber hot mix top coat. And they're using the material specifically because they know it's going to last longer than conventional materials, and since they have the 30-year concession to maintain this road, they're doing everything they can to eliminate future maintenance. So to bring this back around, as far as greenhouse gas reduction with asphalt rubber, I touched on some of the broad brush aspects of it, and in doing a literature search here in preparation for this talk, I referenced the fact that, in fact, George Sousa and George Way, along with Doug Carlson with the RPA, in 2009 published a paper that documented that CO2 was reduced 234 tons per lane mile over conventional materials. And that study was published in their 2009 symposium proceedings. But you see other authors, increasingly in recent years, documenting the various CO2 reductions based on various parameters. And one of the, in addition to this, an interesting papers published in 2012 by the University of California, Davis Pavement Research Center documented the improvement in the rolling resistance of vehicles under pavements that were had smoother pavement. So again, smoother pavement, less rolling resistance, less fuel consumption, therefore less greenhouse gas emissions. So, and we say, and this is important because, or as I say in my Spanglish, porque why? We have our future generation. These are our grandkids. Actually got some more on the way. But Aiden, Christopher, and baby James are looking forward to a long life on a green planet. So I thank you for your time and attention. Again, I appreciate being here. If there are any questions, I'd be happy to take them.